energetics. So this assignment, it's related to the chemical energetics and the bond enthalpy. The first 48 questions are already recorded, so I'll start with question 49. In this question, sodium hydrogen carbonate decomposes on heating to form sodium carbonate, carbon dioxide, and water. The reaction 1 is shown. Suggests why it is difficult to measure the enthalpy change for this reaction directly. Remember, for the reactions which are endothermic, it is impossible or it is really difficult to know how much energy, like because this is an endothermic reaction. So when the reaction is endothermic and we have to continuously supply the energy and we have to decide that when the reaction will complete. So that is a difficulty. We can identify, like we can pass this carbon dioxide through a lime water, it turned milky, and then if no further change is there, or we can collect the gas given off. It can be done, but practically it will have a greater difficulty because when you're supplying the heat energy, the volume of a gas which is given off at high temperature, as a gas expand, as we increase the temperature, so it won't be accurate, or it will be difficult to measure. Usually what happens, the reaction is endothermic, so it will be difficult to measure the temperature change when the solid is decomposing or how much heat energy is supplied. So this is a structure answer. The reaction is endothermic because it is a thermal decomposition. So as a result, it will be difficult to identify when the reaction is complete, or it will be difficult to measure the temperature change, or amount of energy supplied. So you can mention any one of them. I just specify three. First point, you should mention it's an endothermic. Then any one of them you can mention. The enthalpy change can be measured indirectly using the enthalpy change following of the two reaction, like sodium carbonate react with hydrochloric acid, and then sodium hydrogen carbonate react with hydrochloric acid, and sodium carbonate react with hydrochloric acid. In an experiment was carried out to measure the enthalpy change of a reaction 2, this reaction. 100 cm cube of 1.2 mole per dm cube hydrochloric acid was placed in a polystyrene cup and beaker with a capacity of 200. Look, we are using 100 cm cube, but the capacity of the beaker is it's approximately double the capacity or amount of the acid used. So what is a reason for using this large beaker or a container? So what might happen, that the acid might spit out or splash out from the container when the reaction happens. So for the safety purpose, we keep this large container. So this is to minimize the risk. So explain why a beaker used in experiment 1 is large. So it will minimize the risk of so it minimizes the risk of acid splash out from the container. That's the advantage, like minimizing its risk. Show by calculation hydrochloric acid present is in excess. So how we can show it is in excess? The ratio is 1:1. 8 gram of sodium hydrogen carbonate. So if you want to find the moles of sodium hydrogen carbonate, NaHCO3, moles equal mass in gram over molar mass. Mass in gram is 8. Molar mass of sodium hydrogen carbonate, sodium is 23. Hydrogen is 1, carbon is 12, and oxygen is 16 multiplied by 3. Sorry. So that will be 84. And when we divide, we get 0.095. To get the moles of HCl, so moles of HCl, moles is concentration times volume. The concentration of hydrochloric acid is 1.25 and the volume is 100 cm cube. We have to convert into dm cube. So we get 0.125. So the ratio is 1:1. As you can see from the equation, the ratio is 1:1. So 0.095 and this is point. So it means that moles of hydrochloric acid are more from the ratio, because 1 mole of sodium hydrogen carbonate requires 1 mole of hydrochloric acid. But we have more than this. It means hydrochloric acid is in excess. Calculate the energy transfer and hence the enthalpy change. Include the sign. So use the equation energy Cm delta T. And how much is the temperature change? The lowest temperature, the initial temperature was 21.5 and the lowest temperature was 14.2. So that will give us the temperature difference. And whenever we calculate the enthalpy change, we always use a limiting reagent. So if we need the enthalpy change, it is energy divided by moles. How to work out the energy? It is 100 into, but that will give answer in joule. Always convert into kilojoule. So we do it separately. First, we'll get the energy E. So it will be 100 because volume of the water which is used or the solution 4.18. We, and what is our assumption here? Our assumption is that the specific heat of the solution is same as the specific heat of the water. And the temperature change, like the difference which was originally 21.5 and 14.2. This will give us the temperature change and this will give us the energy in joules. For the mass, look, it is a volume. If two solutions are there, if two solutions are mixed with each other, then we'll take the mass, like this mass, which we took is 100, because the formula is E is equals to Cm delta T. If two solutions are there in the question, then you will add the volume of the two solutions and that will be the total mass. But if one of them is a solution like here hydrochloric acid and another one is a solid, in that case you won't take the total mass, you will just take the volume of the solution. The volume of the solution will be same as the mass of the solution. Don't add the mass of the solid in that. So we get this one 3000 and 3051.4, but that is in joules. We have to convert into kilojoule, divide by 1000. So 3.051 kilojoule will be there. And to get the enthalpy change is energy divided by moles. So if you want the enthalpy change, the delta H, energy divided by moles, so energy is 3.0514 divided by the moles. Which mole we'll take? Because there were two moles. One was sodium carbonate, another one was so we will divide by the moles of sodium carbonate, which was in excess, which was a limiting, sorry. So 0.095. So when we divide, it will be about 32 kilojoule per mole. Now, as you can see, whether it's an endo or exothermic reaction, you can see the initial temperature. Initial temperature was 21.5 and the final temperature is 14.2. So means the temperature has decreased. So if the temperature has decreased, it means that this reaction is endothermic. If it was an exothermic reaction, the temperature of the mixture or the temperature of the solution will increase. Is it clear, this one? Now, so the enthalpy change for a reaction 3 can be found, was found to be minus 36.3. Now complete the Hess cycle by adding the appropriate arrow and the formula to outline. So here we have sodium hydrogen carbonate. It gives sodium carbonate plus water. This is a reaction 1. So this is delta H1. So then what might happen? Sodium hydrogen carbonate might react with hydrochloric acid. If it react with hydrochloric acid, so the product will be sodium chloride plus carbon dioxide plus water will be there. And the equation must be balanced, so 2. So this will give 2 NaCl. And this will be aqueous. Water will be there, 2 water molecule. That is, I'm using the equation which is already given. Or what might happen? This sodium carbonate might react with hydrochloric acid. This might react with hydrochloric acid to give the same product. For a Hess law, the overall energy change is independent of the route or the path we follow. Like this is delta H1, this is the first. Delta H2 is for sodium hydrogen carbonate reaction that we worked out, and delta H3 is for the hydrochloric acid one. Like sodium carbonate react with hydrochloric acid. So this one is delta H. This is delta H1. This one is delta H2 and this one is delta H3. Now, how to identify the start or the end of the cycle? Where the 2 arrows are pointing out, that is the start of the cycle. So where the 2 arrows are pointing out, so here the 2 arrows are pointing out, that is the start of the cycle. And where the 2 arrows are pointing in, that is the end of the cycle. So if we follow any route, like we follow route 1 or we follow route 2, the overall energy change is independent of the route or the path we follow. So we can say delta H1 plus delta H3 is equals to delta H2. If we need delta H1 is a subject, so it will be delta H1 is equals to delta H2 minus delta H3. What is delta H2 that we worked out in the previous one? It was 32 kilojoule per mole. And another thing, if you see, when we worked out the enthalpy change per mole, for 1 mole, the delta H2, as we worked out here, this was the enthalpy change per mole for 1 mole. But here, how many moles are used here? How many moles of sodium hydrogen carbonate are used? Because when we calculated for each mole, for 1 mole. This is, we calculate for this equation, for 1 mole of sodium hydrogen carbonate, the enthalpy change for that reaction. But now, we have 2 moles, so this delta H2 will be twice. So this will be twice the delta H2 minus delta H3. So this was about 32 kilojoule per mole minus and delta H3 is minus 36.5. So minus 36.3. So minus 36.3. This will be 64 plus 36.3. So that will make 100.3 kilojoule per mole. So this will be 100.3 kilojoule per mole. Is it clear? Why we multiply this factor by 2? Because according to this, we have 2 moles. But when we calculated in the previous one, we calculated for a single mole. Equation was for a single mole, not for 2 moles. Is it clear, this one? Any doubt in this? The next is question 50. Cordless hair styler uses 2-methyl propane as a fuel. 2-methyl propane react with oxygen on the surface of a heated catalyst. Draw a skeletal formula of 2-methyl propane. So prop means 3 carbon, 1, 2, and 3. And second position, we have a methyl. So this will be a 2-methyl propane. When the hair styler is switched on, the catalyst is heated using battery. Suggests why the battery is not needed after catalyst has been heated initially. Why? Look, as you can see, it involves oxygen. Like it's look like a combustion reaction. And what are combustion reactions? Combustion reactions are exothermic. Means it releases energy to the surrounding. So when the reaction is exothermic, exothermic reaction, it releases the energy. So the point you have to mention, you will mention the reaction is exothermic, and exothermic reactions give out energy. And as a result, it will heat up the catalyst. So initially we need the battery to heat up a catalyst, but once the reaction started, then the reaction is itself is producing enough energy, so we don't need any catalyst. Sorry, we don't need any battery for continuation. The standard enthalpy changes for formation of these compounds are shown. The standard enthalpy change of formation of a water is minus 241. Suggests why this is less negative than the standard. So standard value is minus 285. But when we calculate the enthalpy change of formation of a water in a gaseous state, it is less. So what might happen? Look, if we produce water in a liquid state and we produce water in a gaseous state, this energy was less negative. This energy was more negative, like more exothermic. So what might be a reason for that? The reason is that both are actually producing the same amount of energy. Like both are producing like minus 285, my negative shows it's given out. But what will happen out of minus 285, some of the energy is absorbed by the water, and that water has actually converted into a gaseous state. So when the water, so some of the energy is absorbed by the water, which convert the water into vapor. That's why the overall energy change will be less negative. So energy is absorbed by the water to change the state. And as a result, what will happen? It will become less exothermic. Use the data in the table, calculate the standard enthalpy change of a combustion show your method, you may involve use a Hess cycle and include a sign and units. What is given to us? Formation is given. When formation is given, what the cycle should look like? You will have a reactant, you will have a product, and you will have the element. Element will form the reactant form the product, is same as element directly form the product. So what are the reactants for this reaction? Reactant and product, like the equation, the standard equation is there. This is the equation for C4H10 plus 6.5 O2 gives 4 CO2 plus 5 H2O. These are the reactant and the product. And then what link we will add? We'll add a link which is element. So when formation is given, we add elements. So carbon, we need 4 carbon. We need 5 hydrogen molecules. And we need 6.5 oxygen. Reactant form product, element form reactant, or element directly form the product. Where the 2 arrows are pointing out, that is a start of the cycle, and where 2 arrows are pointing in, that is the end of the cycle. This is the formation of C4H10. The formation of C4H10 is minus 134. Because 1 mole is formed, so minus 134. Then this is what we don't know, like this is what we are finding. This is a formation of carbon dioxide and water. But how many moles of carbon dioxide and water are formed? And which state the water is formed? It's in a liquid, so we have to take this. So carbon dioxide minus 393.5, but how many moles of carbon dioxide? 4. Plus water 5 moles are there. And the formation of a water in a liquid state, minus 285 multiplied by 5. So if you, according to Hess law, the overall energy change is independent of root. So element form reactant form a product will be same as element directly form the product. So it will be minus 134 plus delta H is equals to minus 393.5 times 4 plus minus 285 multiplied by 5 times 5. This minus 134 will move other side. This will give us the enthalpy change for a combustion of this 2-methyl propane. Which is minus 280, minus 870 about, or 869. So delta H will minus 2868 kilojoule per mole. So this will be negative, this will be negative, and then added there. So the final answer will be in negative. So it's 2868 kilojoule per mole. Is it clear, this one? How we worked out? There's also another way when a formation is given. So you can also use, when if the formation is given and you need the enthalpy change. So overall enthalpy change, like formation of a product minus the formation of reactant. You can also do that and you will work out this, it will give. So the enthalpy change of a product minus reactant, you can, if formation is given, product minus reactant. If combustion is given, reactant minus product. That will give us the enthalpy change as well. Refill canister for cordless hairstyle hold 15 grams. Calculate the enthalpy, calculate the energy in kilojoule which can be obtained from one canister. So how we can work out, we have the enthalpy change here. for one more. Delta H is there, which we calculated. So first, like we have this delta H. Delta H is how much? It was our last answer, like 2865 example, kilojoule per mole. Means 1 mole will give 2865 kilojoule of energy. If we have 15 grams, how many moles are there? So 15 gram more. If we need the moles, mass in gram over molar mass of C4, like methyl propane is there. So C4H10, that will be 58, because 12 multiplied by 4, 48 plus 10 makes 58. So this will give us the moles, that is 0.258. So if 1 mole is giving this much energy, so if we have 0.258 moles, how much energy will be there? X cross multiply. So value of X will be 2865 multiplied by 0.258. This will give us how much energy will be released in kilojoule. It's about 740 kilojoule from one canister. The enthalpy change of a reaction can also be calculated using a cycle below. Calculate the enthalpy change of reaction using this cycle. Look, first, where the two arrows are pointing out, that is the start of the cycle. Where the two arrows are pointing in, that is the end of the cycle. So this is one route. This is what we need, delta H. So we can say delta H plus 11280 is equals to 8410. This will move other side. So delta H will be 8410 minus 11280. So value of a delta H from this one, and this was minus 2870. So minus 2870 kilojoule per mole. The enthalpy change of vaporization of a water was once one piece of data used to calculate the enthalpy change shown beside the arrows. What other information we need? Like enthalpy change of vaporization of a water is one of the things which we need. What else we need? Like we should know the bond, the enthalpy changes. We should know the bond enthalpies as well. Like bond enthalpy means like how much energy is released or how much energy is needed to break these bonds. Here we are producing so because like carbon hydrogen will react and they will form or C4H10 will C4H10 is a 2-methyl propane. So what else, what information we need for this energy to calculate? So we need the bond energy for carbon-carbon, we need the bond energy for carbon-hydrogen, we need the bond energy for oxygen-oxygen, we need the bond energy for carbon and oxygen. Like we need all the bond enthalpies. So for this one, we required the bond enthalpies or bond energies for hydrogen bond, carbon-carbon bond, oxygen carbon, and hydrogen oxygen, because all these bonds are present in reactant and product. So we need bond enthalpies to calculate the overall how much energy will be released. Because if you remember in IGCSE, we used to calculate the bond breaking minus bond forming will give us the enthalpy change. So for that, we need the bond breaking energy and bond forming energy. Here, so we need the bond energies for all of these reactants and the product.